Hello everyone, this is a challenge question walkthrough for Edexcel's Core Pure Year 1 textbook, Chapter 3. Okay, this first question is from exercise 3a, and we're given this sum here, and we're told it's equal to 0, and we need to find the value of n. So, just to start with, the first thing to note here is that this sum goes from r equals n up to 2n, so we need to split this sum up into the sum from r equals 1 to 2n. And then from there, we need to take away the extra sums that we don't need, which are from r equals 1 again, up until n minus 1. So we're left with just from n to 2n. Okay, and we know this is equal to 0. So now we can split these sums up as we used to. So the sum from r equals 1 to 2n of 12. Then we're going to take away 2 lots of the sum from r equals 1 to 2n of r. And then we're going to take away, now we've been careful with negatives here, we're going to have the sum from r equals 1 to n minus 1 of 12. And then we're going to take away 2 lots of the sum from r equals 1 to n minus 1 of r. And the reason why I put brackets there is because we need to be really careful with negatives. So we're going to have a negative for this first sum, and then because we're doing a negative times a negative, we're going to add this last sum there. Now we can just work these out one by one. So this first one here, the sum from r equals 1 to 2n of 12, which is going to be 2n times 12. So summing up 12 2n times. Then here we're going to have 2 lots of the sum from r equals 1 to 2n of just r, which is n, which in this case is 2n, n plus 1 over 2. Then we're going to take away the sum from r equals 1 to n minus 1 of 12, which is just n minus 1 lots of 12. And then this last bit, we're going to add on 2 lots of the sum from r equals 1 to n minus 1 of r, which is n minus 1 times n minus 1 plus 1, which is just n over 2. Okay, and doing some simplifying here, we have 24n, the 2's here cancel, so we're left with just minus 2n, 2n plus 1. Then we're going to have minus 12 lots of n minus 1. Then again the 2's cancel, so we're left with n minus 1. And simplifying further, we have 24n minus, now if we expand the brackets, 4n squared minus 2n, and minus 12n plus 12, plus n squared minus n is equal to 0. So now if we go up here, collecting like terms, we have minus 3n squared, then we're going to have 9n, then the constant term is just 12. Dividing through by minus 3 gives us n squared, minus 3n minus 4 is equal to 0. Factorizing to give us n minus 4, n plus 1 is equal to 0. Gives us two solutions, n equals 4 and n equals minus 1. And because in this sum here we're going from r equals n up to 2n, we're expecting n to be less than 2n. So we're going to have n being positive. So we can ignore this solution and we're left with n equals 4. Okay, for exercise 3b, part A asks us to find polynomials f2 of x, f3 of x, and f4 of x, such that for every n which exists in the natural numbers, the sum from r equals 1 to n of f2 of r is equal to n squared. Sum from r equals 1 to n, the sum of r equals 1 to n of f3 of r is equal to n cubed, and the sum from r equals 1 to n of f4 of r is equal to n to the power of 4. Now this looks very scary, but essentially what they're asking us for is to reverse engineer the processes you've been learning in this chapter. So we want a polynomial f2 of r such that when we sum from r equals 1 to n of this polynomial, we're going to get n squared. Well, we know that the sum from r equals 1 to n of r is equal to a half n plus 1, which is equal to a half n squared plus a half n. So we know that 2 lots of this is going to give us n squared plus n. Okay, and again we could just write the 2 inside the bracket, reverse engineering the process. So this is the same thing as the sum from r equals 1 to n of 2r. Okay. Now we want just n squared to be the sum, so we need to somehow get rid of this n. And we can do this by using another standard result, which is the sum from y equals 1 to n of just 1 is going to be summing up 1 n times, so just n. So if we want n squared, then this is equal to the sum from r equals 1 to n of 2r, which is this, and then we're going to take away the sum from r equals 1 to n of just 1. And again, we can combine these sums to give us the sum from r equals 1 to n of 2r minus 1, and that is going to be our polynomial f2 of r. So that's for part A. For the second part of part A, we're going to do a similar sort of thing. Let's have a look at what the sum from r equals 1 to n of r squared is, because that's going to give us something in n cubed. So this is a sixth n plus 1 to n plus 1. And if we expand these brackets out, then we get 1/6 n, and then these two brackets give us 2n squared plus n plus 2n, so plus 3n plus 1. So we get 1/3 n cubed plus 1/2 n squared plus 1/6 n. Now to get the n cubed that we want, we're going to multiply both sides by 3. So we get the sum from r equals 1 to n of 3r squared is equal to n cubed plus 3/2 n squared plus 1/2 n. And then just as before, we need to get rid of this 3/2 n squared and 1/2 n that we have left over. We can do that using a similar process. So to get rid of this n squared, we can start with the sum from r equals 1 to n of just r, which gave us 1/2 n squared plus 1/2 n. So again, we need to multiply both sides by 3 to give us the sum from r equals 1 to n of 3r is equal to 3/2 n squared plus 3/2 n. Okay, so then we can take away this sum from the blue one. So if I do that here, we're going to have the sum from r equals 1 to n of 3r squared, take away 3r. We're going to have n cubed plus 3/2 n squared minus 3/2 n squared, cancel, and then 1/2 n, take away 3/2 n, gives us n cubed, take away n. And again, n we can just write as the sum from r equals 1 to n of 1. So we have that the sum from r equals 1 to n of 3r squared, take away 3r, plus 1 gives us n cubed minus n plus n, which leaves us with just n cubed. So for f3 of r, our answer is going to be 3r squared minus 3r plus 1. And I guess technically what the question is asking for is the polynomials in terms of x. So really we should write this as f2 of x is equal to 2x minus 1, and f3 of x is equal to 3x squared minus 3x plus 1. Okay, and for the last part of part A, we're going to do a very similar thing, starting instead with r equals 1 to n of r cubed to give us a quarter, lots of n squared, n plus 1 squared. So this gives us a quarter times n squared plus 2n plus 1. Expanding out, we have a quarter n to the power 4 plus a half n cubed plus a quarter n squared. Now, to get the n to the power 4, we need to multiply this by 4. So we have the sum from r equals 1 to n of 4r cubed gives us n to the power 4 plus 2n cubed plus n squared. Now going backwards again and looking for a way to eliminate this n cubed, we're going to have the sum from r equals 1 to n of r squared, which is a sixth n plus 1 to n plus 1. And expanded just like we did last time, we're going to have 2n cubed, so that gives us a third n cubed here. Then we've got 3n squared, so a half n squared. Then the last part is just n, so we have a sixth n. Okay, and now we can multiply this through by 6 to get the 2n cubed we want. So this gives us 2n cubed plus 3n squared plus n. And then we can take this away from the red sum down there. So the sum from r equals 1 to n of 4r cubed take away 6r squared is now equal to the n to the power 4. The two n cubes cancel. We've got plus n squared, take away 3n squared, take away n. So we've got n to the power 4, take away 2n squared, take away n. So now let's use the sum from r equals 1 to n of r, which is a half n plus 1, or a half n squared plus a half n. And we can multiply this through by 4 now to get the 2n squared we need. So we have 2n squared plus 2n. Now we're going to add this onto the last sum to get rid of this minus 2n squared. So our new sum is r equals 1 to n of 4r cubed minus 6r squared. And we're going to add on 4r to give us n to the power 4. The 2n squareds cancel. The minus n plus the 2n. So this is n to the power 4 plus n. And the final thing we need to do is just take away that extra n. So for the sum from r equals 1 to n of 4r cubed minus 6r squared plus 4r, then take away the sum from r equals 1 to n of 1, will give us just the n to the power 4. So our final polynomial, f4 of x, is going to be equal to 4x cubed minus 6x squared plus 4x minus 1. Again, for part B, hence show that for any linear, quadratic, or cubic polynomial h of x, there exists a polynomial g of x such that the sum from r equals 1 to n of g of r is equal to n lots of h of n. Okay? So, if we let this h of x just be a general cubic, so that's ax cubed plus bx squared plus cx plus d, then this covers all the cases for linear, quadratic, and cubic polynomials. And we are asked to show that there exists some function g of x such that if we sum from r equals 1 to n of that polynomial g of x or g of r, then we're going to get n lots of h of n. So if we will just quickly see what n lots of h of n is, that's a n to the power 4 plus b n cubed plus c n squared plus dn. And we need to show that we can choose some polynomial g of x such that when we sum it from r equals 1 to n, we're going to get n lots of h of n. And they're asking us to show this after having done part A, using the word hence here. So somehow we need to use our answers from part A in this part. And the way we can do it is we can say, well, I know that the sum from r equals 1 to n of f of 2 of x is equal to n squared. And the same for f3 of x being equal to n cubed, and f4 of x being equal to n to the power of 4. And of course we know that the sum from r equals 1 to n of just 1 is equal to n. Okay? So we can write what we need here as the sum from r equals 1 to n of, well, to get n to the power of 4, we need f4 of x. We need a lots of it to get a n to the power of 4. Then we need b lots of f3 of x. Then c lots of f2 of x. And then just d. And that will give us a lots of the sum from y equals 1 to n of f4 of x plus b lots of the sum from y equals 1 to n of f3 of x plus c lots of the sum from y equals 1 to n of f2 of x, and then plus dn. And from part A, this is going to be a n to the power 4, then we'll have bn cubed plus cn squared plus dn, which is equal to n lots of the polynomial h of n. And that is, and so we've shown, yes, there definitely does exist a polynomial g of x, and we know it's equal to a f4 of x plus b f3 of x plus c f2 of x plus d as required. And finally, for mixed exercise 3, we're asked to show that these two sums are equal to the expressions on the right hand sides. So if we start with part A, first of all, we've got the sum from I equals 1 to n of the sum from r equals 1 to I of r squared. Now, if we work out what this inner bit is first, so the sum from r equals 1 to I of r squared, or using the standard results, we know this is equal to a sixth. And because we're going from r equals 1 to I, we're going to use I as a variable. So a 1/6 lot of I times I plus 1 times 2i plus 1. And if we expand this out, we get 1/3 I cubed. Then we're going to have 1/2 I squared and 1/6 I. And now we're going to input that into the sum on the outside here. The sum from y equals 1 to n of 1/3 I cubed plus 1/2 I squared plus 1/6 I. And again, we can split this up into standard results. So if I do that down here, this is equal to the sum from I equals 1 to n, or 1/3 of the sum from I equals 1 to n of I cubed, plus 1/2 times the sum from I equals 1 to n of I squared, plus 1/6 of the sum from I equals 1 to n of I. And now we're in terms of n, so we're going to have 1/3 times 1/4 n squared, n plus 1 squared. Then we're going to have 1/2 times a sixth, n plus 1, 2n plus 1. And finally, 1/6 times 1/2, n plus 1. And now if we quickly examine these terms, then we can see that each of them, well, the constant part is actually equal to a 12th for all of them. And we also have a factor of n that we can factor out on each, and also n plus 1. So if we factor out 1/12 n plus 1, then we're left with n plus 1 for the first term, then 2n plus 1, then just 1. And if we expand and collect like terms in this last bracket here, we're going to get n squared plus n plus 2n, so plus 3n, then plus 1 plus 1, which gives us 2. That factorizes to n plus 1, n plus 2. So we're going to have 1/12 n plus 1 squared, n plus 2, as required. Okay, and finally for part B, we've got a very similar thing here, but with 3 sums instead of 2. So if we first work out what that inner sum is, so the sum from r equals 1 to I of r, that's just going to be in terms of I, 1/2 I plus 1, or 1/2 I squared plus 1/2 I. And putting that straight into the next outer sum, so the sum from I equals 1 to j of 1/2 I squared plus 1/2 I. Then again, using standard results, just as we did before, we can have 1/2 lots of 1/6 I plus 1, 2i plus 1, and 1/2 lots of 1/2 I plus 1. Okay, and if we expand the brackets here, we're going to have, for the first part, 1/2 times a sixth times 2i cubed, so that gives us 1/6 I cubed. Then we're going to have 3i squared, which gives us 1/4 I squared. Then we're going to have just I, so that gives us 1/12 I. And for the last bit there, we're going to have 1/4 I squared plus 1/4 I. Collecting like terms, 1/6 I cubed stays the same. We've got 1/4 I squared plus another 1/4 I squared, which gives us 1/2 I squared. And then 1/12 I plus 1/4 I is going to give us 4/12 I, which is just 1/3 I. Now finally putting that into the last sum on the outside, the sum from j equals 1 to n of, now we've got 1/6 I cubed plus 1/2 I squared plus 1/3 I. And again, using standard results, 1/6 times 1/4, n now, n squared, n plus 1 squared. And we're going to have 1/2 times a sixth, n plus 1, 2n plus 1. And finally, 1/3 times 1/2, n plus 1. Okay. And now if we look at the answer we were expecting to get, they've got 1/24th out the front. So if we factor out 1/24th, then we're going to have, and again noticing that in each of the terms we have n and n plus 1. Then we're going to be left with n plus 1. Now this next constant here is 1/12th. So to factor out 1/24th, we need to multiply by 2 here. So we're going to be 2, lots of 2n plus 1 for this term. And the last term, we've got 1/6 as a constant, so we need to multiply by 4 on the inside. And that's all we're left with. Now the last step, just expanding brackets and simplifying. For this last bracket, we're going to have n squared plus n plus 4n, so plus 5n, and plus 2 plus 4 gives us plus 6. And this last bracket here factorizes to n plus 2, n plus 3. So we're left with our final answer, 1/24th, n plus 1, n plus 2, n plus 3, as required. And that is the end of the challenge questions for chapter 3. I hope you enjoyed this video, and I'll see you soon.